This lesson, entitled Solubility Equilibria, covers some sections in Chapter 16 of your textbook. We're going to be looking at our final example of equilibria. It's an application of equilibria where we're looking at how substances dissolve in water. Some key definitions from grade 11 that are important are that a solution is a homogeneous mixture with one or two more substances dissolved. And the key classification of solutions is that a saturated solution contains the maximum amount of solute dissolved at a given temperature for a given amount of solvent. Unsaturated has less than the maximum amount of solute, and a supersaturated solution has more than the maximum amount of solute. When we're dealing with solubility equilibria, we are studying saturated solutions, and the equilibrium reactions that we study and the constants are for a saturated solution. Now, last year you looked at the solubility rules, and we were studying equilibrium at that solubility at that point in a qualitative way. So we would look at whether or not a precipitate was formed given a particular combination of reactants. Now, this is still a very useful list, and it's one that needs to be memorized for the qualitative study of chemistry and for reactions. What we're going to be doing this year in our quantitative study is examining the fact that the precipitates from the solubility rules are actually what are referred to as slightly soluble salts. Because the reality is everything will have a certain amount of solubility in water. It's just a matter of how soluble it is. And the ones that are considered insoluble using this table have very low solubility, as you will investigate. Now, when we're looking at the equilibrium for a solubility equilibrium, what we are looking at is the salts that we're studying and how it dissolves in water. So this is the opposite of how we would consider reactions in grade 11. In grade 11, we would consider the double displacement reactions that led to the formation of the precipitate. So for example, in this first one, we might have had silver nitrate, which is soluble, reacting with sodium chloride, which is also soluble. And in the double displacement reaction, we produce AgCl, which is our precipitate, and the soluble sodium nitrate. So in grade 11, you examined these reactions and you created a net ionic equation. And the net ionic equation that you would have produced from this particular reaction is that AgCl is formed by the reaction of Ag plus and Cl minus. So when we're studying reactions qualitatively, this is how we would look at a precipitation reaction or forming a precipitate. When we're studying solubility equilibria, we are studying the solubility of a particular salt. So the ability of this salt to actually dissolve or break up into its ions in solution. So that's why we think of the equilibria as being the solid in equilibrium with the ions, so that we can imagine the solid going into solution. Now the equilibrium constant expression for this reaction is the concentration of Ag plus times the concentration of Cl minus. As you know, the solid, being a pure substance, is not included. And these equilibria are referred to as Ksp, where Sp stands for solubility product. So this is referred to as the solubility product constant. The reaction that you studied in the lab formed lead iodide. So when we're studying this equilibrium, we study the dissolving of lead iodide in water to form ions Pb2 plus and 2I minus. So when we're studying solubility equilibria, we need to be very mindful of the ratio of the ions in the solution because that will affect our Ksp expression. So this is the concentration of Pb2 plus times the concentration of I minus squared. We need to apply the coefficient as we would in a regular equilibrium. As I mentioned before, it's important to recognize that this gives the relationship of the concentrations of the ions in a saturated solution. So when we have an equilibrium, we've got a saturated solution. Okay, so we've got the maximum amount of ions dissolved before we see a precipitate forming. Now, table 16.2 in your textbook gives you a list of the solubility products for some slightly soluble salts. What you'll notice is that the substances that are listed here are ones that the solubility rules would have led you to call insoluble in water. And if you look at the values of the KSPs, you'll notice that they're very, very small. So these are slightly soluble salts, and we're studying a very small quantity being able to dissolve in solution. Now, because the KSP represents the saturated solution, it is also a good indicator for whether or not a precipitate will form. Just like in our original equilibrium unit, we examined the expression Q. Okay, we called it the reaction quotient. In solubility equilibrium, we call this the trial ion product. Okay, so it's a product that we sub into when we don't know whether or not we're at equilibrium. So we call that Q. So if we're trying to decide if a precipitate is going to form, you'll see in the problems that we solve for Q, and then we compare the Q value that we've solved for to the KSP. If the Q is equal to the KSP, we've found a combination that leads to a saturated solution. If we have a Q that's greater than the KSP, we know that a precipitate will form. There are simply too many ions to stay in solution. And if the Q is less than the KSP, then no precipitate forms, or we're left with an unsaturated solution. A few other key terms: the difference between molar solubility and plane solubility. Molar solubility, when you're being asked for it, you're being asked for the mole per liter, the amount of moles of solute that can be dissolved in 1 liter of solution. And when we're talking about solubility, we're talking about a saturated solution. So it's maximum solubility. If you're just being asked for the solubility in grams per liter, that's the number of grams of solute that can be dissolved in 1 liter of saturated solution. Now, last year, you'll recall that you were looking at solubility curves, and you would have the solubility in grams per usually 100 milliliters, okay, on the y-axis, and then you would have the temperature in degrees Celsius. And you'll remember you did questions that asked you, there was several curves on it, and it asked you for various scenarios, whether it was a saturated, unsaturated, or supersaturated solution. And the values along the curve represented saturated solutions. Anything above was supersaturated, and anything below was unsaturated. So you were looking at solubility in grams per 100 milliliter. These two flow charts will help you to go between solubility and the KSP of the compound. So if you're given the solubility, this will help you to flow to the KSP of that compound. And if you're given the KSP, this will help you to flow to the solubility of the compound. And you might stop at molar solubility depending on the question that you're asked. The best thing for us to do here is to do several problems so you can see the various types of calculations you can do involving KSP. So the first type of problem is when we're given the solubility and we're asked to find the KSP. So we're given here that the solubility of copper hydroxide is 1.72 grams per 100 milliliters at 25 degrees Celsius, and it asks us to determine the KSP. Now, in order to determine the KSP, we need to be working with the molar solubility. So what we're going to do here is first change the solubility that's given to us in grams per 100 milliliters to a molar solubility. So the molar mass for the copper hydroxide is equal to 97.57 grams per mole. And what we have here is a solution where 1.72 times 10 to the negative 6 grams of this is dissolved in 100 milliliters. So we can determine the moles, okay, by doing moles is equal to mass divided by molar mass. So the moles that we have here is 1.76 times 10 to the negative 8. To find the molar solubility, we want the concentration that can dissolve in moles per liter. So we've got 1.76 times 10 to the negative 8 moles dissolved in 100 milliliters, which is 0.1 liters. So the molar solubility of the copper hydroxide is 1.76 times 10 to the negative 7 moles per liter. We're going to use the variable S to describe solubility. Now, in order to determine the equilibrium constant for this reaction, what we need to do is examine the equilibrium that we're studying here. We're studying a solubility equilibrium, so it is the equilibrium of that solid dissolved in water, and we break it up into its ions. Now, when we are thinking about something dissolving, we're actually thinking about this substance dissolving in water. And it's the solubility that defines the amount of this that can dissolve. Okay, this is the amount of copper hydroxide that can dissolve in water. So essentially, we start with none of this dissolved. And what we do when we study solubility equilibrium, instead of using X, we use S to describe the changes. So this is increasing by S. And this is increasing by 2S. Okay, because if we think about this, I'm going to put it in brackets as S because it's a solid, so we're not actually going to involve it in our calculations. But what we're doing here is thinking about this substance breaking up into its ions. And for every one of these, we put into the equilibrium 1 copper ion and 2 hydroxide ions. Okay, so we're applying the ratio here. So at equilibrium, this is S and this is 2S. So the amount of this that's able to dissolve, because this essentially goes down to 0 at equilibrium because all of it dissolves, it will allow us to know what S is and therefore know what the concentration of the copper ions and the hydroxide ions will be in this saturated solution. So to find the Ksp, we're taking the concentration of the copper ions that we have and the concentration of the hydroxide ions that we have squared. So we know what the concentration of the copper ions is 1.76 times 10 to the negative 7. And the concentration of the hydroxide here is 2 times S, so it's 1.53 times 10 to the negative 7. Okay, and we are squaring that because that's what we need to do based on the equilibrium expression. So what we have here is 2.19 times 10 to the negative 20. It's a very small Ksp value, but it's what we would expect if you look at the solubility. This is a tiny amount of copper hydroxide that can dissolve into this solution. Okay, so it makes sense that we have a very small Ksp value. If we want to go the other direction, so if we're given the Ksp and we want to know the solubility, okay, we need to look up in our table what the Ksp value is. So for this one, we're dealing with barium sulfate, and we look up the Ksp value is 1 times 10 to the negative 10. So barium sulfate, when we're studying it, its equilibrium is barium 2 plus SO4 2 minus. Okay, this is another case in the year where knowing your polyatomic ions is very useful. And when we look at this equilibrium, when we're dealing with solubility, we're starting with none of these dissolved, and then the maximum solubility of barium sulfate is the amount that's actually going to dissolve. So each of these, because they're in a 1-to-1 ratio, will have a concentration of S at equilibrium. So when we sub into the equilibrium law, which is barium hydroxide times sulfate, we're going to have S squared is equal to 1.1 times 10 to the negative 10. So S in this case is equal to 1.1 times 10 to the negative 5, and that's in mole per liter. Okay, so when you solve for the traditional X from your ice charts, what you're actually determining is the solubility in moles per liter of the particular substance. For zinc hydroxide, it's a little bit different because we have a ratio other than 1-to-1. When we look at zinc hydroxide, we get Zn2 plus 2 hydroxide. And for these, they're all the same. So if you want to skip ahead to just the ice chart, the E row, okay, this is going to be S and this is going to be 2S. Okay, your ions always start at 0 and always increase in the ratio that is reflected in the equation. We have S and 2S. The key here is that we've got this 2S and we also have a Ksp expression that considers that 2S. So we've got zinc times hydroxide squared. So we're going to have S times 2S all squared, which is 4S cubed. When we look up the Ksp value for this, we find that it is 7.7 times 10 to the negative 17. When we solve for S here, we get 2.68 times 10 to the negative 6 moles per liter. So the solubility here is in moles per liter. So this is the molar solubility, but we're asked for solubility. And what you need to assume is that if you're just asked for solubility, that it's asking you for the grams per liter. So if we want to find the solubility in grams per liter, we need to take the S and multiply by the molar mass of the zinc hydroxide, which in this case is 99.41. And we find that we get 2.66 times 10 to the negative 4 grams per liter. Okay, so example 1 and 2 are going from Ksp to solubility and solubility to Ksp. The next type of problem that you can answer is one where you predict whether or not a precipitate is going to form based on a particular scenario of reactants and products. So in this example here, we're adding 2 milliliters of 0.2 molar sodium hydroxide to 1 liter of calcium chloride, and it's asking us if a precipitate will form. So I find for most people, looking at the double displacement reaction is the easiest way so that we can get rid of our spectators and look at what we're dealing with. So we've got sodium hydroxide and calcium chloride. This will make sodium chloride and calcium hydroxide. Okay, and so this is our double displacement reaction. Now the precipitate that we're actually dealing with is this one here. Okay, so the equilibrium that we're going to be studying is the calcium hydroxide equilibrium. Now we are mixing 2 milliliters of the sodium hydroxide and with 1 liter of the calcium chloride. So what we need to do is figure out the concentration of the hydroxide and the calcium ions that are going to be in the solution. Okay, so when we dilute this, we've got sodium hydroxide with a concentration of 0.0004. And, you know, sodium hydroxide dissociates in a 1-to-1 ratio. Okay, so we know the concentration of the hydroxide is 0.0004 in this reaction. For the calcium chloride, okay, we've got a dilution of 0.0998, okay, and this breaks up into calcium ions and chloride ions. So the concentration of the calcium here in a 1-to-1 ratio is still 0.9998. The equilibrium reaction that we're studying is of calcium hydroxide dissolving in water. Okay, so what you have here is an initial scenario where we've got 0.0998 of calcium and 0.0004 of hydroxide. And essentially the question we're being asked is this system at equilibrium? Is it a saturated solution, or do we have more or less than a saturated solution? And that's how we decide if we've got a precipitate. So just like in previous units, if you want to know if something's at equilibrium, you need to find Q. And in this section, we call this the trial ion product. Okay, so I'm going to take the calcium concentration, I'm going to take the hydroxide concentration and square it. And I am left with 1.597 times 10 to the negative 8. Now the Ksp for this reaction, which you can look up, is equal to 8 times 10 to the negative 6, which is less than, so our Q is less than our K, okay? Therefore we get no precipitate. Okay? If the Q was equal to the K, we would have a saturated solution. If it was larger, a precipitate would form, but because it's smaller, we know that we have fewer ions in solution, so they are able to stay dissolved. In this second example, I'll do a shorter solution to this one. Okay, but when you look at the double displacement reaction, you find that the equilibrium we're studying is of zinc hydroxide. Okay, so we've got this equilibrium, and the Ksp is given in the question, and the Ksp is 7.7 times 10 to the negative 17. When you examine the dilutions, what you find is that the hydroxide concentration, okay, provided by the sodium hydroxide in the solution, is 0.15. Essentially, the volume has doubled, so the concentration has halved. Okay, same for the zinc. Okay, its concentration is halved. So those are the concentrations of zinc and hydroxide in this solution when it's combined. So when you look at what the Q is, it's 0.05 times 0.15 squared, and that's equal to 0.001125. In this case, since the Q is larger than the Ksp, okay, a precipitate will form. You've put more ions in the solution, okay, than the water that you have present can actually accommodate or dissolve. Okay, so it's above a saturated solution, and we see a precipitate forming. In the acid-base unit, we dealt with the common ion effect as our study of buffers. And what we're going to look at now is the common ion effect and how it affects solubility. So how does the presence of a common ion affect the solubility of a salt? In this first example, we're going to compare the solubility of AgBr in pure water and in a solution of 0.001 molar NaBr. So the equilibrium that we're studying here is AgBr. If we've got it in pure water, when we look at our ice chart, essentially we start with 0. So we've got 0 plus S plus S. So the solubility of this is found by using S squared is equal to the Ksp. So it's equal to 8.77 times 10 to the negative 7 moles per liter. So in pure water, we're starting initially with no ions. In our second example, we want to study the solubility of AgBr in a solution of 0.001 NaBr. Okay, and as you know from the solubility rules, NaBr is soluble, so it dissociates completely. So what essentially we're putting into the solution is 0.001 of Na ions and 0.001 of Br ions. Sodium ions, being spectators, don't affect the equilibrium at all, but the Br minus, by having those in the solution, will affect this salt's solubility, because initially we don't have 0 ions of Br, we've got 0.001. So the Br minus here is the common ion. So when we look at this, and if you think about it in terms of Le Chatelier's principle, this Br minus is going to hinder the solubility of the AgBr. Now, because the Ksp value is 7.7 times 10 to the negative 13, we can make the assumption here, so this is really just the same as 0.001. So what we have here is S times 0.001 is equal to 7.7 times 10 to the negative 13. So we find the solubility in the sodium bromide solution is 7.7 times 10 to the negative 10. So in comparing them, you can see that the solubility has decreased, due to the presence of the common ion of Br minus. We can also examine the pH of a saturated solution and the effect of changing the pH on the solubility of a substance by looking at a hydroxide. Okay, so if we examine the hydroxide, copper 2 hydroxide, the equilibrium that we're studying is this one here. Okay, and we want to determine the pH of a saturated solution. So a saturated solution has maximum solubility. So really what we want to do is determine the solubility of copper hydroxide, and that will allow us to know the concentration of the hydroxide in the saturated solution. So for this one, we've got 4s cubed is equal to 2.2 times 10 to the negative 20. So S here is equal to 1.77 times 10 to the negative 7. So that's the solubility of the copper hydroxide in a solution that's saturated where this amount of copper hydroxide has been dissolved. We've got twice as much hydroxide, so the concentration of the hydroxide being equal to 2S is equal to 3.53 times 10 to the negative 7. The question is asking us for the pH, so we find the pOH equal to 6.45 and the pH equal to 7.54. The other part of the question is what will be the effect of increasing or decreasing the pH on the solubility. If you increase the pH, you're essentially increasing the concentration of the hydroxide ions in the solution. So if we think about this in terms of Le Chatelier's principle, if I increase the hydroxide, it's going to shift it left and it's going to decrease the solubility. Okay. If I decrease the pH in this particular equilibrium, that's going to decrease the hydroxide, because if I'm decreasing the pH, I must be adding some acid, which is going to have a side reaction with hydroxide and lower its concentration. If I lower the concentration of the hydroxide, Le Chatelier's principle tells me that this reaction is going to shift to the right. And as it shifts to the right, I am increasing the value of S in this particular reaction. Okay, so that concludes our discussion of the calculations that involve